Welcome to today's lecture of SSD. I just see that I still have to open this. Yes, now we can also see the slides. I can also see the slides, I hope. And that's where we continue. The Menti code should still be the same as last time, so we are just continuing to use the same Menti. Then we continue now with the presentation of introduction and low level. Okay. So that I see your questions, I will also open the same Menti again. Will the slides be available on the EIK homepage? Yes, after the lecture I will upload them to the website. Okay, let's start. So you might have heard of Rust, right? And it's one tweet that I found quite nice. Fun fact: Rust is basically just an extremely slow explosion, and then a comment to it: if you need a faster explosion, use C++. Yes, of course. Let's talk about low-level stuff, and there you very often need C++. And Rust also has these interactions with low-level code, and in those situations it's also difficult to make Rust really safe when working with low-level interfaces. We will talk about privileges and context switches, we will talk about memory layout and ELF, we will talk about calling conventions and also C++ classes. So this part is a bit of repetition from operating systems. You might know that already, but it's relevant for SSD because you want to write exploits, and there it's important to know about these things. So let's start with privileges and context switches. So when you think back to operating system, you configured the memory through page tables with read permissions, with write permissions, maybe non-executable if it's already supported on the platform that you are targeting. 64-bit platforms usually have a non-executable bit. There are separate configurations for different processes and also one for the kernel. And when you perform a context switch, this is quite interesting. When you schedule a new thread, you act as if the thread was already running and we are just returning from an interrupt. And this is interesting. Why? Because in some exploits, you will manipulate the stack and make the operating system or some user space program also believe something. And there it's very helpful if you know how the hardware uses the stack or the registers during these context switches. So we first restore the CPU register values. We push the stored register values to the stack. We modify the registers with that. The IRET instruction that we use for that expects these values on the stack. ASP, eFlags, CS, and EIP. In 64-bit mode, it's the same. With IRETQ, then it's again the stack selector, RSP, the stack pointer, RFlags, the code selector, and then RIP for the 64-bit instruction pointer. Then IRET pops the register values, these ones, from the stack into the registers, and with that it changes the instruction pointer and we continue at this new instruction pointer. That's basically how we schedule a thread. When we switch from an old thread to a new thread, it's basically even easier to imagine how it works. This is only caused by an interrupt. Right? We always, when we switch from one thread to another, this is caused by an interrupt. There are some special mechanisms like syscall, sysenter, but other than that, it will always be an interrupt. Then the CPU pushes some registers onto the stack, exactly the ones that we've just seen. Then we will store the register values, maybe in some struct in the kernel to conveniently use it. For that, we push the CPU registers on the stack because otherwise we would modify registers already if we directly access the struct. With this, only the instruction pointer and ESP are modified, which we already have saved up here. And then we will copy all the CPU register values from the stack into a struct. The old thread then continues executing the scheduling code. So the scheduler is actually executed by some thread. And then we context switch to the new thread as before. If there are any questions on context switches, just ask them in the Menti and I will then pick them up. Now we get to one part that I really like, the memory layout and ELF. Didn't we cover that part already? I think I showed you this part already, right? The address space layout. So if you've seen that already, just leave me a message in the chat. Then I know that I can continue here, because I thought I already presented that. If not, I will just repeat it. So we have this 64-bit address space. Yeah, I think we had that last time, right? So we had this address space, and the non-canonical part is the largest part. But if we zoom in the user space, we have these different sections. And I think we also mentioned those. And also there we had the PLT, the GOT, and we also took a closer look at these regions. Now I'm a bit confused by what I added here in these slides, because some of the parts that I have in this slide deck I definitely did not cover. So let's maybe continue right away. Yes, we also had this trampoline code and everything. This is not the part that I was looking for. Let's see. Yeah, here we continue. Here is where we continue. Okay. Yes, this was our assembly program that we stepped through last time. And this time we will talk about further features of this language. So in 32-bit mode, we have the cdecl calling convention. In 64-bit mode, we use the system v ABI. And these two calling conventions define how arguments are passed to functions. And this is particularly important for variadic functions. So with variadic functions, you know them like printf, scanf, where you can provide an arbitrary number of arguments. In those cases, you have to, the compiler has to know a way how to get those arguments from the stack. And in cdecl, it's super easy. In cdecl, it's push all the arguments in opposite order on the stack. In 64 bits, in the ANV 64-bit ABI, we first fill the registers, and then we push all the remaining arguments in opposite order on the stack. So then it works pretty similar. But first we fill all the registers, or at least a certain number of registers. Okay. We will, last time we already looked at function execution. We will look at more function execution this time, but also at C++ and use classes there and how classes interact with each other. How does the function now know? Let's think about it. How many parameters we have? For instance, with printf. We have printf. We push all the arguments in opposite order on the stack. How do we know how many parameters there are? Does something like exec also use this for spawning entire new programs in their first thread? I'm not sure whether this is still referring to the context switches. If yes, then yes. The other question, exec, there are exec variants which also are variadic functions that take an arbitrary number of arguments and then pass them as an argv array to the new program. So yes, exec also uses variadic functions. And there again, how does exec know how many parameters? which data types. Or for printf. For printf, you can pass arbitrary data types there. How does printf know which data types and parameters you pass? It doesn't, does it? If it doesn't, well then how does it know how many elements to read from the stack? Or from registers? It just pulls the data, so it just pulls the data from the stack when calling printf. That's basically what happens. So printf, we have the format string here, and the format string defines what printf does. We are basically programming printf here, and printf will now parse this format string and pop from the stack a character, then an unsigned integer, a float, and then a character pointer. And if they are not on the stack, then it will just pop anything from the stack that is there. And this makes format strings, of course, very powerful, because now you can do what you like with format strings. Okay, let's see. I'm trying to make the light a bit more balanced here. Okay, so let's see. Yeah, what if format string and data on the stack do not fit together? Yes, then hopefully you get a warning, sometimes not even that. Yes. Printf doesn't know, yes, exactly. It just follows whatever this format string says. So if this format string is nonsense, then it will also pull nonsense from the stack. I don't think at any point it actually counts how many arguments it has or had. It's just offset. Yeah, basically, so you can imagine it like a loop or a state machine that printf runs through, and it iterates over this format string, and yeah, will just go element by element and pop this from the stack or from the registers. So it has to store, for the calling convention, the compiler has to generate some code there to handle that. But the compiler knows which registers are filled with which data. Okay, so let's talk about the call stack. So what do we put on the call stack? Maybe local variables, maybe function arguments, but what is always on the call stack when calling a function? The return address. And if you have many nested calls, then we have many return addresses, and that's of course a great target for exploitation. Great. Okay, so any questions so far on calling conventions? Otherwise, I would directly proceed with C++ classes, and that's probably, I think that's the last big topic we have for today. So it's, I tried to fit this lecture in on Friday, but it, yeah, we couldn't fit that in anymore. So we don't have that much content today. So it should be fine. Let me just check whether I have anything after that. No, that's, yes, that's the last part that I need to present to you. And then we are ready for the exploitation topics. Okay, so C++ classes. Basically, C++ class objects are structs in memory. If you would look at a memory dump of a program, you would find that C++ objects, well, you find the member variables there, maybe some other meta information that is stored for the object, but it's basically a struct. Also, if you use structs in C++, they are very similar to classes. just with the difference of the visibility of member variables. So structs have default public visibility. C++ classes not. So a struct, basically struct in memory. Structs contain all the member variables, including any member objects or parent objects. Well, maybe pointers to the parent objects. What does this refer to? So if we are talking about whoever created this object, then maybe it should be a pointer, maybe some reference. But if we're talking about a class which is derived from something else, and that's meant with parent, then also, yes, this object has to be contained in this object, any object that we are deriving our object from. By default, pointers for methods, they are very interesting. So the first time I saw them with the debugger, I was a bit confused why they look like that. Methods, so pointers for methods. Okay. Here it says function pointers. There are some differences that you will see between pointers for methods and function pointers. And these pointers for methods are not stored in the object. They are just used implicitly by the compiler, but there is one important exception: virtual methods. If you have virtual methods, and that's the part that I was referring to, that can be pretty confusing at first, but we will clear that up now. Virtual tables. Virtual tables, VTables, are a great feature that I think might be the most important feature of C++. The feature to use classes and enable polymorphism. You have a base class, you derive classes from that, and now you can refer to them with the base class or base class pointer and use methods that they have in common. So virtual tables are a fundamental feature that enables this. It's basically a table with function pointers. And the VTable is very commonly the first member of every object. But of course the compiler could change that. But in GCC, for instance, it's the first member of every object. Then the idea here is, if you have a table with function pointers, that a specialized class, a derived class, can simply override the previous function pointer, and by that, you know that you have to call another function. Implicitly, you don't even have to look at this up. So let's take a look at this example. I implemented this example. We have a class here, animal, with constructor, animal print. This should be a print method, print animal constructor. It has a virtual method make sound. That's pure virtual. It's not, there's no implementation provided here. And then we have the move method. It says moving. Okay, prints moving, doesn't do anything else. Then we have the animal destructor, and it just prints the message. Derived from animal is bird. Bird also has a constructor. It prints bird constructor. It has a make sound method, and this one prints cheap. So the sound that a bird might make. And then we have the bird destructor, which prints bird destructor. I also have this class here, cat, and it's also derived from animal, cat, and then we have a cat constructor here. We print cat constructor. Then we have the make sound method here, and the make sound method. Again, these are all virtual, right? And this is again printing a message, a different one than for the bird. So the cat makes meow, the bird cheeps. And then we have our move method, which is also implemented here. This is the difference here between the bird and the cat. So the cat has a different move. It says prowling. And then we have the cat destructor. And then we can see what happens if we compile this and see what the compiler makes of it. Here's our main program. We have an animal B, that is a new bird. Then we have the animal C, that's a new cat. Then we call make sound once and move once and then delete both. So let's see what happens if we step through that. We step into this bird constructor, that's the start. We construct this bird object and we get a VTable for this bird. And this VTable has two entries. And when you call a method in this object and it's a virtual method, then the function, so if you print this in a debugger, you might just see this value somewhere instead of a function pointer. And that's always the case if you're using the VTable, then you will only find this offset into the VTable there. So the bird constructor is called, the bird constructor is executed, but when the bird constructor is called, it also sees, okay, it's derived from animal, so we will also call this constructor, and this constructor has to be executed. And here we see that now the VTable for the class bird is now initialized with the methods that we already have from animal. That's the first thing that happens because the animal constructor is executed. The make sound method is initialized to 0, pure virtual, and the move method is initialized to some valid address because we already have it here up there. The next step is we go back to the bird constructor. So we printed our animal constructor message now. Now we go into the bird constructor, and the bird constructor will now override some of these entries if it has an implementation for that method. The make sound method, for instance, now it's overwritten with this function pointer that we have here. Oh, that's interesting. So the VTable is actually pretty simple. Okay, let's see. We constructed the bird, go back into the main function. Now we construct the cat, and the cat again gets a VTable. We have our constructor here. It again has to call the animal constructor, initializes those two methods. And in the next step, we are done with the animal constructor. We now will execute the cat constructor, and both methods here are replaced with the methods of the cat. The next step is, well, we execute these methods, and although both are animal pointers, it's now super clear why they can execute different methods here. Although make sound is looking the same, right? It's, in both cases, it's an animal pointer, and in both cases, it's the make sound method. It's clear that from the VTable, they will just call different functions. That's the entire magic behind a class hierarchy. And that would be super trivial for you to implement also in C if you would have to implement object-oriented stuff in C. Okay, so this is the VTable. We have the make sound method here. Now the one for the bird is executed. We print this message and we go back into the main function. For the cat, we also have the make sound method. And we execute that one because it's referenced in the VTable again. Then we call the move method. The move method, now for the bird, we didn't have an explicit move method. So this one would use the one from the animal class. So what happens? It will pick up this. So here we reference the VTable entry number 1, pick up this address here, jump there, print this message. That's basically it. In the next step, we go back to the main. We execute the move function of the cat, and the cat again picks up this method that is written in here in the VTable and executes that one. In the last step, we delete those objects, and there we can also check what happens. I placed virtual in front of those, but I didn't write virtual here, and I wanted to see what happens, whether the compiler makes a difference there. So let's see what happens. We first delete the bird, so we execute the bird destructor. It executes the animal destructor. So the bird destructor is executed, animal destructor is executed, and then this VTable is also deleted. For the cat destructor, we see that exactly the same thing happens because it's derived from animal and therefore both have to be executed. How that is implemented, in some cases you will find that the VTable has standard entries for the destructor, for instance, and they are added on top of the methods that you define as virtual. Okay, and then we return from the main, and that's basically it. The last part that I want to show you is a signal example. Yes, I like this signal example, but before we go to the signal example, stay a bit here, and if you have any questions, just post them in the chat or in the Menti. There's one question in the Menti. I will pick that up. Let's see. Open Q&A. No, I don't see it on the phone yet. Just give me a second. I need to reload sometimes. Do other programming languages like Java or Python still use a VTable to handle polymorphism? I haven't looked that up, but they would need some mechanism to find the correct method to execute. So I would expect that they have a similar mechanism there in place. And now I need to mark this as answered. So the VTable is part of the animal class. The VTable is also part of the bird class, and in some cases you might even have more virtual methods in the derived class, or actually very often you would have more virtual classes in the derived class than in the base class. And the compiler has to make sure that in the VTable there's enough room for all the virtual methods from the base class and from the derived class. But the compiler knows that because the compiler can look up the code. So there's no difference between a virtual in front of a destructor and no virtual before it. I'm not. Well, I think there's no difference. No, I think destructors are always virtual, but I'm not. I might be wrong here. But I executed this code example, and at least in this code example, it didn't make any difference. Is the VTable calculated once per class or subclass on startup or lazy loaded? So the VTable is okay. So the VTable, I think I read something that there are different approaches. Maybe it was even on Windows versus Linux, or maybe it was compiler, maybe the Microsoft compiler versus GCC. And I do remember that some of them have only one central VTable and some of them put them in the object. And I think GCC puts the VTable in the object. I'm pretty sure it does. Yes. Is there only one VTable? I think there are compilers that have this optimization, but I'm pretty sure that it's not the GCC that has this optimization. In the chat, so Ferdi writes in the chat, destructors aren't always virtual, but all classes that have virtual calls need to have virtual destructors. Otherwise, delete X would call the wrong destructor. Yeah, that makes a lot of sense. Yes. Okay. Let's continue with this signal example. This one, I really like this signal example. So, the signal example that I'm going to show you illustrates what you can do with signals, and this can be very useful for exploits. The example that I'm showing you is well, is interesting, and maybe it's relevant for security, but also it's just an example to illustrate how to use signals. Signals are very powerful. You can use them for communication between processes, to send that some event occurred or trigger some interaction. They are a bit similar to exceptions, and sometimes they are used for exploits. So what we are working with here is, I wrote this code. So this is a simplified example of the code. I removed a few printfs and debug things, and also this is just an if. I also in the code that I will show you in a second, this will be a loop. So what we have here is in the main. So this is basically the idea that I have. I basically check, okay, I have some number, and the number is not the largest number that fits in 64 bits divided by 4 kilobytes. Okay, why that? Well, that would also be the highest address we can represent, divided by 4 kilobytes for one page. So the highest page number, virtual page number that we have in our system. If it's not the highest page number that we have in our system, I starting maybe at 0, then we print the state. We say the last state is the current state. We increment I. Okay, so we go one virtual page number further. We set the current state to valid, and then we dereference this address. Virtual page number times page size. So we just dereference this address with volatile size t pointer. Dereference it. Any problems here? Before I show the next step, any problems with this code? I will be initialized to 0, and then we go here, and then what happens? And the next part is, well, that's not kernel space. We are in user space. I'm running that in user space. So this will be a regular user space program, and I will be accessing addresses like 0, then address nullx 1000, then address nullx 2000, nullx 3000, and so on. I will access every page in the virtual address space. What's the problem? What will happen? It will fault, absolutely. We will get a seg fault. And this is the part that you would have liked to know in ESP or SEP back then, where you got point deductions when your code seg faults. And that is this signal handler. Signal is exactly seg fault handler. Whenever there's a seg fault, you just catch it. Isn't that great? So what will we do? Seg fault handler. Whenever we get a seg fault, control is transferred here. And then we say current state is invalid. Well, this address was apparently not valid. And then we unblock this signal, the seg fault signal. Oh, great. Unblock signal, I also put the code here, but that's just copy pasted from, I think, from the man pages. So what we do here is we have our signals, we create an empty set, we set the signal number in this set. So we create a set mask here, and basically use that to tell this sigproc mask function that we want to unblock all the signals that we have added into this set, and that's only this zigzag v number. So with that, we can unblock our seg fault handler again, and then we can have another seg fault. That means we can have more seg faults. Okay, let's see. So we dereference the null pointer if I is 0 exactly, and we will take a look at what this does. So let's take a look at this. I will add one more thing here, and that's this one here. So when I wait a second. When I'm executing now this segfault handler, I have the problem that I need to go back into my code, right? I want to continue looping through that. And there's the part, it's really nice. You probably have heard of goto, and I'm a big fan of goto. You should use goto for error handling and not exceptions. Exceptions are super awful and you shouldn't use them. But goto is nice. Goto can be the best practice for error handling. But you have to use it in a beautiful way, of course. Goto is nice because it's structured. You cannot use goto to jump from one function to another. With exceptions, you can, which is super ugly. And another function, another method that allows you to do that, that is more unrestricted, as goto used to be many, many years ago, and before the C language, long jumps. In some languages, goto is unrestricted. You can jump from any function to any function. In C, this would be long jump. Long jump, I wouldn't use that. In C, the goto keyword in C, that's a super structured and restricted goto that is fine to use in many contexts. So we have the long jump here, and here we have a set jump. What does this do? Set jump sets a label basically for our long jump. We have a variable where we store our address in, and then later on long jump can be used with this buffer to jump back to this location in some completely different function. In the chat, Ferdi says there are some implementations that implement exceptions with set jump, long jump. Yes, that's also why I call exceptions basically just long jump wrappers. So if you want to use long jump in your code, because you're like, I don't know, I use long jump all the time in my programs, it will be fine. And then someone says, oh, you shouldn't use long jump. Just use exceptions. No one will notice, right? That's how exceptions work. So how does it work? Set jump, we set jump here, and then we have our if, we go in there, we print the state, last state is current state, increase this, and then we dereference the first address, and maybe this is 0. So let's assume this is 0 now, or maybe it's 1. Both will crash, right? Ferdi says in the chat, modern implementations actually do more than that, though. Of course, if you want to implement exceptions properly, then you also have to consider all the stack unwinding. You might have to call destructors. It's super complicated. Yes, I agree. So the background is still, so the reasoning why I really recommend to avoid exceptions is still that no matter how much it does on top, it still just wraps a long jump in the end. So what does buff jump do? So set jump buff, that's a variable where we store the address in where we currently would be. So buff is basically the label. Long jump to buff, that's the jump to the label. So what happens when we dereference this invalid address now? We get a segfault. We get a segfault, that means control is handed over here. We set the current state to invalid, we unblock the signal, then we go through this, unblock the signal, we use the long jump and jump back here to the set jump and continue from there. Great, we implemented a loop with long jump. Very nice. Okay, and then it continues like that. Let's take a look at this in a live demo. Okay, so I have to hide the slides for that, and I have to open some editor for that. I should have some C code for exactly this example. Yes, let's take a look at this example here. I will just show it to you in a second. You just have to select the VS Code in here. Yeah, you should be able to see that now. So this is the code. I added some more stuff around. The segfault handler is still here with exactly the things that I told you that are in there. The unblock signal is exactly here as I described it. Just here I added a bit more logic around so that I iterate through the address space in a nicer way. I also made this a loop because not all addresses are segfaulting, and I want to continue also for these that are not segfaulting. I also made the printfs a bit nicer, but it's basically the same code as on the slides. Okay, let's see what happens if I run this. GCC signal, I don't know, minus, do we need anything like that? Let's try what happens. Oh, it doesn't like me. Some warnings because I'm doing weird casts. But let's just try what happens. So if this works, we should be seeing maybe a segfault and then a printed message for that. And for each segfault, there would be one update in the line because I'm rewriting the line here. I'm using some code for the terminal to rewind the line, and then we write it again. So this should be a nice way to print the invalid regions, and we would see then the lower end should stay the same. The upper end should run up until we find a valid region, and then it will skip until it finds the next invalid region. And of course, most of the address space will be invalid. So let's run this. And here you can see it. Oh, that's pretty fast. Yeah, let's maybe move that somewhere up here so that it doesn't get in the way. Yeah, this will run for some time. Okay. That's a lot of faults per second. A lot of segfaults per second. Oh, is this going to find anything? It says all the memory is invalid. Of course, because there's a very long time until we find the first valid region. But I can do one trick here. I can compile this with static, and I know that static on Linux should still disable ASLR, and then we should find then we find a valid addresses much sooner. So we can see now which ranges of addresses are valid and which are invalid. So, yes, a virtual space scanner. That's right. Yes, the 64-bit address space is large. Yes, that's absolutely correct. Yes, it will take some time. How long will it take? Well, we have 2 to the 48 bits. We would have to skip the non-canonical region because that's just useless to scan. So then we have 2 to the 48 divided by 2 to the 12. That would be 2 to the 36. That would still run for some while. So let's check the Menti, because we are, this is just some brief lecture today because we wanted to cover it actually on Friday but couldn't fit it in anymore in the 2 hours. So we are already at the end of the topics for today. And so I'm just taking questions now. Off topic, do you have any information on when we will get the individual repositories for the KU? No, I don't have that because I'm also not that much involved with the KU. So I don't know that actually. Just ask someone from the KU, maybe on Discord. Any more questions? If there are no more questions, then I can let this run forever, of course, but then I will at some point stop this and basically, tell my computer that it had enough segfaults already. There's another question. Is there a deadline for the lecture hacklets, or can they be done at any time? You should finish them before the first exam. So before the first exam, when the first exams, I think it's the day before the first exam. After that, it would be tricky for us to take that into account because you can also solve the lecture hacklets during the exam, and then it would be a bit weird which of the points we now take. So you have to, the cutoff is before the first exam. How is the last address calculated? It says, so not minus ULL. ULL is just the data type. Let's just scroll a bit up in the VS Code. So I will. So the last address is, while I is not minus I ULL. So minus 1 ULL. So what does this do? Minus 1 is, if you think about the number, in principle, a number where all the bits are set, right? Take 0. If you decrement by 1, then all the bits in the entire register will be set, and the entire number will be set. Now with U and LL, with LL, I define that I want to have a 64-bit number. So it will not be just a 32-bit number where 32 bits are set to 1, but 64 bits. And with U, I define that it should be interpreted in an unsigned way. So although I wrote minus 1 as a long, so it's 64 bits set to 1, with unsigned, I say, well, it should be interpreted as an unsigned variable. And that means that it's the largest number that we can fit in 64 bits. Divided by 4096, then it's divided by page size, so the last page that we have in our system. Is there a recommended order for the hacklets? Recommended order for the hacklets. I don't think there is necessarily, but you can of course ask other students that have already started how they started, with which hacklet they started, and they might give you a good idea. Okay. So I have never worked for Amazon. So as I understood, we can submit multiple solutions for each hacklet if we do not get the flag on the first upload. Yes, that's correct. That's absolutely correct. You can do that. Sounds good. No more questions? Well, then I would say we are at the end of the lecture, and on Friday we continue with the first exploits, and that's where I think Martin will take over. So have fun with that, and then see you later this semester, by the latest for the exam.